So today I'm going to be talking about Lab 5, Magnetic Braking with Faraday. So start off with the introduction. The purpose of this lab is to showcase both Faraday's laws and Lenz's laws by inducing a magnetic current as well as a magnetic field with the use of a cylinder composed of aluminum foil to effect acceleration. Therefore, we will be dropping a magnet through an aluminum foil to calculate and test Faraday's laws of induction. So the physical principles that we're going to be using are Faraday's laws, as shown by this image, Lenz's laws, as shown by the image on the right, as well as Newton's second law, Newton's third law, the Biot-Savart law, as well as Ohm's law in some of the analysis. The experimental data, we have a length of 0.28 meters, a width of 0.015 meters, and a radius of 0.0125 meters, and an average time of 3.6 seconds. So, in terms of systems and surroundings, the system is going to be the bar magnet as well as the roll of aluminum foil, and the surroundings is the Earth. Possible errors in this experiment could be due to the inaccuracies of the measurements of both the tube as well as the time it took for the bar magnet to fall, and this could be due to human error largely. So here we have the first section of the code. In this section of the code, we establish the dimensions and measurements of the components, such as the aluminum foil in this experiment, as well as the fact that we are going to be establishing the ring segments as stacked in the y-axis. For the second part of the code, we're going to be establishing the size and dipole moment of the magnet, as well as establishing the magnetic field of the bar magnet. In this third part of the code, we're going to be establishing the d flux over dt for the falling magnet, as well as establishing the simulation loop, which is the motion prediction and visualization. For the fourth part of the code, we're going to be calculating largely the B field of the ring based on a asymmetric magnetic field. For this final part of the code, we're going to be calculating the net force as well as the magnetic force on the magnet, as well as the magnetic velocity and position, which is what we were finally trying to calculate, as well as plotting a velocity versus time graph for the magnet as it drops and printing data. Yep, and here are the code results. Now, here are also the results as shown when we run the program, showing the MET at the top, as well as the velocity versus time graph, as well as the printed code. So the interpretation is the computational model is red, therefore red must be counterclockwise with blue being clockwise. This is based on the fact that the induced current must be in the counterclockwise direction because the North Pole was facing downwards. The dynamics of the system is if the magnet was flipped, that would cause the induced current to flip directions. However, the flux would be constant, therefore the motion of the magnet would be identical to how it was before. The computational model is likely accurate as it does not suffer from any form of human error and it doesn't have to face any resistive forces like air resistance. The shape of the velocity versus time plot shows us that we will eventually reach a terminal velocity based on the fact that these forces will all eventually balance out. So the what if. What if the resistivity of the conductor was reduced to as close as possible to zero? Then based on the Ohm's law of V equals IR, the current would increase as the R decreases to keep a constant voltage, which would cause the magnet to move slower through the tube as there would be a greater resistance due to Faraday's law due to the increased current. So what if holes or slots were cut in the tube? Then there would be less rings and therefore less induced current and less induced magnetic force on the magnet, which would cause it to fall faster due to there not being a counteractive force. And here's the final conclusion. As shown earlier, length of 0.28 meters, width of 0.015 meters, and a radius of 0.0125 meters, average time of 3.6 seconds, which is different than the compared value of 3.7 seconds. So, based on this conclusive model, we have a very, very similar average time that it took to drop compared to the 3.7 seconds that we received in the computational model. However, the predictive or computational model differs based on the fact of human error, miscalculations in mu, as well as just errors with timing and the dropping of the magnet not being instantaneous. So that's what we have based on our conclusion. Thank you.